Okay. We have a skier weighing 62.9 kilograms. He's at a height of 123 meters. He's going down the ski hill that has an angle of 14.1 degrees. The coefficient of friction on here is 0.121. I want to know how far on the level surface will he go before he stops. And the friction on the bottom is 0.623. This looks like a scary question, and a question that you guys might want to know for the test. So let's see how I do. And he's moving with an initial speed of 12.9 meters per second. So, at the top, he's got a certain amount of energy. What kind of energy does he have? At the top, he has kinetic energy because he has a speed. He's got potential energy because he has a height. So, formula for kinetic energy, 1/2 m times v squared. What does he have energy due to height? He's got mass times 9.8 times his height of 123 meters. Is there any work being done against him? Is there any friction? Yeah. He's got friction on this part, and he's got friction on that part. I'm just going to worry about this part to start with. How would I calculate the frictional force on an incline? I'm going to calculate the force gravity going straight down. Force gravity on the incline, 62.9 times 9.8. 616.42 newtons going straight down. But when we're on an incline, not all the force normal is going to go straight up and down. Some of the force normal is going to go that way. So, I'm trying to figure out the frictional force. I need to find that piece there. If this angle here is 14.1, I'm going to use the cosine relationship. So cosine 14.1 degrees equals the adjacent side over the hypotenuse. So my force normal is going to be 616.42 times cosine 14.1, which is 597.8. Now, if that's my force in the y direction here, that's going to be my force normal there. That will help me calculate my force friction there. Force friction is mu times force normal. My mu on the incline, 0.121. My force normal, 597.8. Therefore, my force friction going down the incline is going to be 72.3 newtons. How does that fit into my whole energy equation up there? It is going to be work, which is force times distance. Now, I found out my force. My force is 72.3. How long does that force act? It acts for this entire length. How do I find the entire length of that side of a triangle? I've got the opposite side. I've got the hypotenuse. I have to use sine. Sine of my angle equals my opposite over my hypotenuse. To get the x by itself, that would give me 123 divided by sine 14.1, 504.9 meters. Now, it definitely makes sense that it would be much longer because it is the hypotenuse. So I go back to my original equation, minus my force, which was 72.3, and my distance, 504.9. That expression here gives me an expression for the amount of energy I should have when I get to the bottom. Energy is not created nor destroyed, it only changes forms, so from this side it would be equal to that side. So let's put that in our calculator. I have 1/2 times 62.9 times 12.9 squared, plus the potential energy it had, 62.9 times 9.8 times 123 meters up, minus the work done against it. And the work done against it by friction would be my force, 72.3, times the distance it acted for, 504.9. So the total energy the skier would have at the bottom of the hill is 44,549 newtons. $44,549 newtons. So that's the energy it has at the bottom. The question is, how long would he go along here until he stops? So this energy here has to be used up by what? By the work of the friction against it. He weighs 62.9 newtons still. His force gravity we calculated earlier to be 616.42. This time, his force normal will be what? Will be exactly the same because he's on a flat surface. 616.42 would be his force normal. To find his force friction on the flat surface, force friction is mu times force normal. I have a different mu on the flat surface as well. It's even stickier on the flat surface, possibly no more snow. Could be rocks, could be anything. 0.623 times my force friction, or my force normal, of 616.42. My force friction on the flat surface is 616.42 times 0.623, 384, which is much, much higher. Now, what is stopping the skier at the bottom? All his energy is being used up by the work being done against him. The work being done against the skier is force times distance. We have just calculated the force. So how long would it take him to stop, or how long would it take him to use up all of that energy? His displacement from the bottom of the ski hill would be 44 1,549 divided by 384. 116 meters from the bottom of the ski hill. It's how long he would coast before he stopped.